The race to power AI data centers won't be decided by which material wins. That's my read on it. What actually decides the outcome is the boundary line. Who takes responsibility for which stretch, from where to where? The next generation power technology just announced by EPC, a pure-play GaN maker, looks to me like a move aimed squarely at shifting that boundary. Today, let's read the shape of a quiet turf war that has already begun. Hello everyone, I'm Ty, with 31 years in the semiconductor industry. In today's video, I'll walk you through the substance of Gen 7, the new generation technology announced by the GaN power semiconductor maker EPC. How three materials, silicon, silicon carbide, and GaN, currently divide up the roles inside an AI data center's power system. And finally, the shape of the turf war now unfolding right along that boundary. My goal is for all of it to click together by the end. As always, let me start by simplifying things into a familiar picture so we can grasp the whole. Imagine a powerhouse team in an ekidon, a long-distance relay race. The course has three different phases. Right after the start comes a punishing mountain road with steep, relentless climbs. The middle is a long, flat stretch where raw speed is everything. And the finish takes you through a downtown maze of narrow, winding streets to the goal. A winning team never makes a single superstar run the entire course. On the mountain road, they put a runner whose pride is raw power and toughness, someone who doesn't fold when the road gets rough. On the flat, they put a speed runner whose leg turnover is simply on another level. And in the downtown section, they put a steady, dependable runner who excels at tight cornering and staying composed. Each one is unbeatable in their own stretch, but step them one section outside it, and they suddenly turn ordinary. The right runner in the right place. That division of labor is the real source of the team's strength. But this year, the organizers announced they were going to reshape the course dramatically. Because the amount of cargo they need to deliver to the finish has grown by an order of magnitude, they're going to make the middle flat section much longer and redesign it so runners can move through it far faster. And when the course changes, the positions of the exchange zones, where runners hand off the sash, inevitably get redrawn as well. So what happens when the exchange zones move? The length of each section changes, and so does the question of which runner covers how many kilometers. The teams that have a speed runner started arguing, on the new course, our ace should be handed a longer section. Once that happens, the contest is no longer a simple foot race between runners. Where you place the exchange zones, the jockeying over that positioning, is what decides who wins. The clever teams start moving before the course change is even officially locked in. They prove their strength through training runs designed around the new course, and they sell the organizers on a section layout where their own ace can shine for the longest possible stretch. Just having a fast runner isn't enough to win. The team that secures the section where its runner shines is the one that wins. From here, let me lay out concretely how this simplified story is actually playing out on the real industrial ground. The lead player is EPC, full name Efficient Power Conversion, a U.S. pure-play maker of GaN, or Gallium Nitride, power semiconductors. On July 20th, 2026, EPC announced that it will showcase its latest generation Gen 7 GaN power technology at PCIM Asia 2026, an international power electronics exhibition to be held in Shenzhen, China from August 26 to 28. The defining features of the Gen 7 generation are low on resistance, low switching loss, and high frequency operation. To put it plainly, there's little loss when current flows through it, and little loss even when it switches on and off at high speed. And when you can switch faster, you can shrink the surrounding components, which means you can build the power supply itself to be smaller and more efficient. This is technology aimed at raising the power efficiency of AI servers. Behind all this is the explosive rise in AI server power consumption. GPU power draw keeps climbing, and if you keep distributing electricity at the traditional low voltage, the current grows too large. The losses and the wiring both start hitting their limits. So distributing power across the whole rack as high voltage direct current in the 800-volt class and cutting the conversion losses along the way has become a critical design approach. EPC's exhibit covers the power delivery all the way from that 800-volt DC down to right beside the chip, the point of load. There are concrete numbers here, too. The evaluation board EPC has announced is a 6-kilowatt isolated DC-DC converter that steps 800 volts down to the 12.5-volt class, with an efficiency of 97% at full load. That works out to only 3% of the input power turning into heat. Converting across that huge voltage gap, from 800 volts down to the 12.5-volt class, at high density within the limited space of a server, this is a world where the raw performance of the power semiconductor translates directly into results. From here, let me dig in from a professional's point of view. On the surface, this news is just a GaN maker announcing a new product. But that isn't what I'm paying attention to. The key point is that GaN is putting forward a configuration in which it takes on high voltage, 800 volts, head-on. To me, this isn't a story about a product. It's a story about coverage, about which material is responsible for which voltage range. In an AI data center's power system, there is no single all-purpose power semiconductor. Today, 3 materials divide up the roles. The entry point, receiving power from the grid side, calls for high breakdown voltage, high power handling, and high reliability. That's SiC, silicon carbide. The middle conversion stage, which demands high frequency, high density conversion, is where GaN excels. And the final low voltage region that feeds the chip is handled by silicon MOSFETs, proven and inexpensive. It's exactly the EPC division of labor: mountain road, flat, and downtown. What matters is that the boundary lines of this division of labor are not fixed. The shift to 800-volt DC distribution is a redrawing of the course, and it redefines who takes responsibility from where to where. The fact that EPC has put forward 800-volt capable 6-kilowatt conversion is, in my view, a move to extend GaN's section toward the higher voltage, higher power side. In EPC terms, it's the speedrunners team raising its hand and saying, let our ace run a longer stretch. So what's happening now isn't a win or lose contest between materials like SiC versus GaN. On the new course, it's a turf battle over where to place the exchange zones. That is, where to draw the boundary lines between the materials. If the boundary moves, the size of the market each material is responsible for can move with it. That's precisely why each company comes to a venue like an exhibition to demonstrate our material can take responsibility all the way out to here. That's how I read it. From here on is my own take. In the world of digital semiconductors, the industry as a whole grew enormously once design and manufacturing became a division of labor. I expect power semiconductors to head the same way. Rather than one material covering every section, the future will demand a division of labor premised on each material's strong section, plus the ability to combine those pieces into a single coherent power system. Having a fast runner and being able to draw a winning section layout are 2 entirely different capabilities. So from now on, when you look at power semiconductor news, try focusing not on which material won, but on which voltage to voltage range is this product aiming at. At PCIM Asia in August, exhibits from many companies will line up side by side, but if you view them through this same lens, what looks like a mere catalog of new products should start to look like a battle map, a deployment chart in a turf war over the boundary lines. This is not somebody else's problem for Japan either. Japan has several companies that have invested in SiC, as well as companies with long track records in silicon power semiconductors. If the boundary moves, some companies will see their section widen, while others will see theirs cut back. Beyond developing raw material performance, the real question is how a company secures its own section within the whole power system of the 800-volt DC era. We're entering a phase where the skill of that turf-taking, not just the technology, is what will be tested. Today's single takeaway is this. The question, which one wins, SiC, or GaN, is framed the wrong way from the start. The correct question is, which section and who runs it? Keep this lens with you, and the growing stream of power-related announcements ahead should suddenly look far more three-dimensional. Let me sum up. EPC, the pure-play GaN maker, will showcase its new generation Gen 7 GaN power technology at PCIM Asia 2026 in August. Behind it is the move to 800-volt DC in AI data centers. That evaluation board, 800 volts down to the 12.5-volt class, 6 kilowatts, 97% efficiency, is a move to widen GaN's section. The competition in power semiconductors is shifting from a win or lose between materials to a turf war over the boundary lines. And the winner, I believe, won't be the fastest runner, but the team that drew the smartest section layout. That's all for today. I'll keep bringing you semiconductor news and analysis, so if you found this useful, please like, subscribe, and I'll see you in the next video. This has been Ty on Semiconductor News Decoded.